Greetings from a hotel room in Louisville, Kentucky. I'm here, but I'm going to talk to you about electrodynamics, about currents that move, as opposed to electrostatics, which we talked about last week. Charges, electrical charges that are more or less where they're going. We're going to talk about circuits and currents that flow, and we already did a lab on lighting light bulbs, and today I'm going to talk a little bit formally about the things that we learned from it. We're going to talk about batteries. We're going to talk about Ohm's law, which is a statement about how resistance of certain circuit elements relates to current. We're going to talk about what resistors are, and we're going to talk about the power dissipated by a resistor. All right, let's start by talking about what a battery is. Then let's shortly follow up by talking about what a battery isn't. A battery, as the lab text said, creates a constant voltage difference between the negative terminal and the positive terminal. Now, what is a voltage difference, and what is voltage? Well, we define it more or less by analogy. Remember when I had you blow through the straws? I said that the thing that caused air current to flow through the straws was the fact that your lungs, the strength of your lungs, created a difference in air pressure between the air in your lungs and the air outside your mouth. When I go like that, that is air traveling from a region of high pressure to a region of low pressure. The amount of air current that flows is sort of a different concept from the amount of air pressure that causes the flow of current. Similarly, electrical currents are caused by differences in electrical pressure. Electrical pressure is voltage, more or less. And when you create a difference in electrical pressure in voltage between two regions, it can cause current to flow from the region of higher electrical pressure to the region of lower electrical pressure. The analogy of voltage to pressure doesn't always help me very much because I'm not sure I have a great grasp on what pressure is, right? I'm not sure that I started off with a great understanding of pressure in my house's plumbing system, but I do have a very good understanding of water currents and air currents. I could imagine standing by a river and saying, oh yeah, that's a lot of current. And so I will draw attention to the fact that voltage is not the same as current. It's sort of a cause of current flowing, and it's analogous to pressure. All right. When I say a battery doesn't create an absolute voltage, I mean usually we will call the negative terminal of a battery, usually we will call that voltage at the negative terminal 0 volts. And then if this is a 1.5 volt battery, that makes this 1.5 volts. But that's not always the case. I could make it such that the voltage at this negative terminal of the battery was 3 volts, in which case, what would the voltage there be? 4.5 volts. Or I could even make the voltage at that negative terminal of the battery be like negative 5 volts, in which case, what's the voltage at that point? Well, a battery's job is to make sure that the voltage at the positive terminal is higher than the voltage at the negative terminal by a certain amount. And if that amount is 1.5 and this is negative 5 here, then this is minus 3.5 volts. It's possible to have negative voltage, just like it's possible to have negative gravitational potential energy like we learned about earlier. This is the circuit schematic for a battery. It's a long line over a short line. You might wonder, how does a battery create a particular voltage difference across the negative terminal to the positive terminal? The answer is chemistry. Moving on. We're not really going to talk about how batteries do their thing. We're just going to say a battery is kind of like your lungs. It creates a pressure difference that causes a current to flow. Or it's like a pump, like a water pump that creates a water pressure difference that causes water current to flow. So let's talk about what this is. What do I have here? There's my circuit schematic for a battery or a cell. And there I've indicated that the strength of this battery is 1.5 volts. There's a delta V, a difference in voltage of 1.5 volts between the negative and the positive terminal. This is a wire. This here is a switch. It can be opened or closed to allow current to flow or not flow. More on that later. This is a bulb. And then here is more wire. So let's talk about the voltage at different locations. I already said that we would usually say that the voltage at the negative terminal of a battery is defined as 0 volts, in which case that would make this voltage 1.5 volts. And what's the voltage here at this location? Well, it's 1.5 volts, and the reason I can say that is that regions that are connected by a wire, here I'm going to close the switch, boom. Regions that are connected directly by a wire have the same voltage, the same potential. So what's the voltage here? 1.5 volts, because it's connected directly by a battery to that location. What's the voltage there? 1.5 volts. What's the voltage there? 0 volts, because it's connected to the negative terminal. What's the voltage there? 0. There, 0. There, 0. There, 1.5. So what this battery does effectively is creates a voltage difference across the light bulb of 1.5 volts. I will also use the word potential or electrical potential to refer to voltage, but note that it is not the same as electrical potential energy. It does not have units of joules. A conductor is an equipotential, same voltage, and locations connected directly by a wire are the same voltage. You might wonder, well, if this is a 1.5 volt battery, but it's going dead, well, does that mean it's really going to just produce a 0.8 volt difference between the negative terminal and the positive terminal? And it turns out the answer is no. A battery is well designed to keep a constant voltage difference for its whole life, right until the life ends and the battery dies, which happens all of a sudden. I asked you during the lab to light a light bulb with one battery, one wire, and one bulb. And I hope that a number of you made an error as you tried to do that. For example, maybe you made this perfectly reasonable error. Well, the battery is the thing with electricity, so I want the electricity in the bulb, so I put the bulb on the battery. But it turns out that doesn't work. And then you might remember back to an earlier 7th grade science class where you remembered, oh yeah, there has to be a circuit, a closed circuit for there to be current. So I'll connect the wire around the battery so that there's a circuit and current flows. Then I'll put the bulb on the electricity. I use the word electricity like I use the word motion. I use it kind of hand-wavely. It's not a very specific term. It's not a term that we'll be using when we talk about physics, unless we're talking about not fully understanding it yet. But neither of these worked. What did it take for a circuit to light a light bulb? Well, we had to route current through the light bulb. We had to have a path that was a closed path that sort of went all the way around some path or some loop. Circuit relates to the word circle, a closed path, in order to have the light bulb light. And so when you did this in 7th or 8th grade, the problem that the teacher asked is, oh, how can you make a light bulb light? And you learned, oh, I have to make a closed circuit. Here, that's not really the purpose of the exercise in this class. Here, the fact that you need a closed circuit indicates something about physics. It indicates that something is continually happening. Something is continually flowing. That wouldn't be possible in this situation or this situation. It wouldn't be possible for charge to continually flow through the bulb in either of these cases without the charge building up in a way that was kind of impossible. What's required is a closed circuit that indicates a continuous flow of charge. So let's talk about that continuous flow of charge. Well, when I close that switch, kaboom, and now charge can flow, which charges flow and in what direction? Well, we had said earlier that it's really only negative charges that flow. Positive charges are sort of stuck in the nuclei of atoms. They are not free to flow. And so I'll tell you actually that it's that electrons tend to move towards higher voltage. So they sort of proceed around the circuit like I'm moving them now. And that is the answer. This is how the charges flow through the wire. The negative charges flow around towards higher voltage. Of course, it happens all at once rather than one after the other, but I can only drag one of these charges around with my mouse at a time. And that's the end of that story. Or is it? The work done on circuits by like Benjamin Franklin and his colleagues, and the work done on electricity back at that time, they didn't know that there were two kinds of charge. They thought there was only one kind of charge that an object could have more or less of. And they also didn't know that the charges that were free to flow were negative charges. And so the model that they developed was of just one kind of charge proceeding in one direction. And they actually thought this. They're like, oh yeah, so these charges fall towards the lower voltage, just like a mass would fall towards a lower height. And so they assumed back in the day that charges proceeded around this way instead of what we now know to be the case, which is negative charges proceeding in the opposite direction. Why am I telling you this? It's because we actually still take this convention. We're actually still using the convention of charge and current flow that was invented before we really knew what was going on, just because so much mathematical machinery and physics machinery was built up around that convention. So in reality, we know that negative charges flow that way. That's the electron current. But we are actually going to, from now on, from this slide on, imagine that positive charges are flowing the opposite direction. We're going to imagine the negative charges are stationary and positive charges are flowing around. It's kind of nicer to think of the movement of positive charges than negative charges, and a movement of positive charge in one direction is mathematically equivalent to movement of negative charge in the opposite direction, so it's okay. But if I say, what direction does current flow in this circuit on a test, there is only one answer, and it is clockwise. It is this way. The current flows this way around the circuit. That is the direction of conventional current. All right. A battery is an example of a device that provides an electromotive force. It is like a pump. EMF is the way we abbreviate electromotive force. And here's a schematic of the circuit that I made above. There's the bulb there. That is the Greek letter epsilon, and it is used to abbreviate electromotive force. The amount of electromotive force that a battery provides is the difference in voltage between its negative terminal and its positive terminal. That's the strength of our electrical pump. So if we have an EMF here, for example a battery, it drives current around this way through the circuit. That is the direction of conventional current. From now on, I'll just call it current. Here's some other things that produce EMF. Battery produces EMF. Solar cells produce EMF. They take solar energy from the photons of the sun and convert it into electrical energy. And it turns out that actually putting a magnet through loops of wire creates an EMF in the wire. That is how most power plants work. They use, say, nuclear fission and take the thermal energy produced from that, use it to boil water, use the rising steam to move turbines that move magnets, permanent magnets, bar magnets, in and out of loops of wire. Or a wind power plant will use the wind's energy to spin around a turbine that will eventually put a bar magnet into and out of a loop of wire to use that EMF. These are some producers of EMF. Now I'd like to talk to you a little bit about current. Let's get quantitative. The current at a location is the amount of charge that flows past that location per unit time. Current, I, is equal to charge, Q, divided by delta T. What are the units of current? Well, I guess it's the unit of charge, which is coulombs. Remember, a coulomb is the unit of charge. It's a very big charge. Per second, that's the unit of time. And a coulomb per second is called 1 amp, or 1 ampere. If you have 1 coulomb of charge passing you per second, that's 1 amp of current. I will tell you that the speed of electron flow through wires is more or less about 1 millimeter per second. Does that seem very fast to you, or does it seem very slow? It seems rather slow to me. I think of current as moving very, very fast. If I turn off my light, and then I turn it on again, I don't have to wait a long time for the electrons to travel from my switch that I pressed to the light bulb, why is there no delay? Well, I'll answer that by using this simulation from our friends at PhET. And what I'm going to do is I'm going to take this, see these blue, we usually use blue for negative charges and red for positive charges. And so this is a, these are electrons in this circuit. When I go like that, boom. Why was there no delay? There was no delay because this wire was already full of electrons. So when this electron over here, right at the switch, started moving, it pushed all of the electrons and it went through the light. Okay, great. So when you put a difference in pressure across a resistor, I'm going to talk about what a resistor is in just a second, you create a current. The straws were an example of a resistor to the flow of air current. When you put the difference in air pressure created by your lungs across the straw, the resistor, it created an air current through the straw. You found that that was true in the lab. Straws resist airflow. They are resistors. The more resistance an object has, the less current you get from the same impetus, from the same cause of current to flow. If you take a long straw, remember, that had more resistance to the flow of air current than a short straw of the same thickness. When you had two short straws side by side, that had less resistance to the flow of air than just one straw alone. This is a circuit schematic of a resistor. A resistor is any object that has some resistance. We had said last week, oh, there are conductors and there are insulators for the flow of electrons. Well, that's not strictly true, we're saying now. An object doesn't simply have infinite resistance when it's an insulator or zero resistance when it's a conductor. An object has some finite amount of resistance, and the amount of resistance of an object can vary along a spectrum. A resistor has resistance. Resistance is a property of an object. A resistor is an example of an object. All right, so the impetus that caused air current to flow was the difference in air pressure created by your lungs. The impetus that causes an electrical current to flow is the difference in voltage created by a battery. It's like a difference in electrical pressure, the EMF of the battery. So if I have a region of higher electrical pressure and a region of lower electrical pressure, that will cause current to flow across a resistor, across something that resists the flow of current. The more difference in voltage you have across the resistor, the more current you get. Just like the stronger my lungs are, the more air current I get. The larger the resistance of the resistor, the less current I get. Just like the higher the resistance of the straw, the less current I get. This is a cause and effect relationship. The effect, current, is equal to the cause, the difference in voltage, divided by some amount of sluggishness, some amount of resistance that an object has to the effect. Have we ever seen something like that before? Yes, we have. Newton's second law, where acceleration was the combination of forces divided by the mass of an object. The effect, the acceleration, was the cause, the combination of forces, divided by the sluggishness of the object. And just in the last unit, we had angular acceleration, comes from a combination of torques acting on the moment of inertia, the rotational inertia of an object. In each case, the effect is equal to the cause divided by some resistance, some sluggishness. Let's talk about electrical resistance. Well, if I solve this equation for R here, I get R equals delta V over I. The difference in voltage between two locations, as the lab handout said, voltage, electrical pressure, is measured in volts. And that's a little bit confusing because we use the same symbol, V, for both the quantity, the voltage, and the unit, volts. The symbol for the quantity current is I, and the symbol for its unit is A, amps. A volt per amp is an ohm. If you apply a difference in voltage of 1 volt across a resistor and get a current of 1 amp through the resistor has a resistance of 1 ohm. We usually write this relationship this way, this relationship I equals delta V over R. Usually we write it like V equals IR, and what I want to emphasize is that this is a statement about a resistor. This is not a statement that would apply to a battery or to a switch or something like that. When we say V, we're really talking about the difference in voltage across the resistor. The difference in voltage across the resistor is equal to the current going through the resistor times the resistance of the resistor. And this is known as Ohm's law, after this dude. I don't know what his name is. It's just a dude. It's Ohm. Okay, quick example. If you have an 8-volt battery and a 4 kilo ohm resistor, what is the current that flows through the kilo ohm resistor? Why don't you pause this video and see if you can write down the answer. If you can do this in your head, you should be impressed with yourself, which means that you should also check it on a calculator or by writing something. What current flows? Pause. All right, here's the answer. Well, there's Ohm's law. If you solve for the current, you get that it's the voltage placed across the resistor. The voltage placed across the resistor, what is the voltage at this location? Well, it's connected by a wire to that location, so this location has a voltage of 8 volts, and that location has a voltage of 0 volts because it's connected by a wire to there. So the difference in voltage across the resistor is 8 volts, just like the battery. 8 volts divided by 4 kilo ohms, 4 times 10 to the 3 ohms, is 2 times 10 to the minus 3 amps, 2 milliamps. And this is about what we get in the lab. Let me just make sure my head is not blocking that. We have in the lab, a typical resistance that you would encounter is kilo ohms or mega ohms. A typical voltage that you would encounter is volts. Notice that our batteries are like 1.2 volts. And so kilo ohms times milliamps equals volts. So what's the voltage there? 8 volts. There, 8 volts. There, 0 volts. There, 0 volts. What's the current through the resistor? 2 milliamps. What's the current through this location? Also 2 milliamps. What's the current through the battery? Also 2 milliamps. We'll talk about the continuity of current more later. All right. You had studied how the length of the straw and the thickness of the straw affected how hard it was to blow through the straw. And was it harder to blow through the long straw or the short straw? It was harder to blow through the long straw. Longer length gave more resistance. Was it harder to blow through the thin straw or the thick straw? It was harder to blow through the thin straw. More cross-sectional area gave less resistance. These effects are combined in this equation. This is the formula for the resistance of a resistor. The resistance of a resistor is dependent on the resistivity of the material the resistor is made of, I'll talk more about that in a second, times the length of the resistor, times divided by the cross-sectional area of the resistor. Okay, so let's say we have a resistor that's made of copper. Actually, it's not great to have a resistor made of copper because copper is very conductive. But you could calculate the resistance of the resistor by taking the resistivity of the material copper times the length of the resistor you're making out of copper divided by the cross-sectional area of the resistor that you're making out of copper. If you were to make it out of nichrome, nichrome is a material that has a different resistivity than copper has. We sometimes use that Greek letter rho to mean density in kilograms per meter cubed, but that's not what we're measuring. But that's not the same as resistivity. What units does resistivity have to have? I'll show you in a little bit. Resistance is a property of an object. Resistivity is a property of a material. When you make an object out of a material, you can make an object out of a material. You can make a resistor out of copper or nichrome. Okay. So let me give you a little simulation of what it looks like to have materials of different resistivities. That's not the one I want. This is the one that I want. Okay, so what's going on here? We've got a battery, and electrons are flowing through the battery from the positive terminal to the negative terminal. The conventional current is going the opposite direction. But these electrons are colliding with stuff inside this resistor. This sort of dark maroon structure is a resistor. And see how like the stuff inside it is colliding with the electrons and kind of slowing them down. It's limiting the current. This pinwheel is there to measure the current. When I increase the resistance of the resistor, more of those cores appeared. What I really was doing, I wasn't changing the length or the cross-sectional area of this resistor in the simulation. I was increasing the resistivity of it. Look at what happens to the current when I lower the resistance. See it going up and up and up. What's going to happen to the current when I increase the voltage of the battery? It increased the current. And we'll talk about this heat later too. All right, that was our PhET simulation on different resistivities. All right, what is the unit of resistivity? Ohms times meters. And here's a little table, just so you know that it exists. The aluminum has a resistivity of 2.8 times 10 to the minus 8 ohms times meters. Tungsten has nearly twice that resistivity at 5.6 times 10 to the minus 8 ohms meters. The inverse of resistance of an object is the conductance of an object. The more an object resists the flow of electrical current, the less it conducts the flow of electrical current. Electrical conductance is abbreviated G, and it is the inverse of resistance, the conductance of an object. If you have an object with more conductance, you get more current across it from the same impetus, the same difference in electrical pressure. This is Ohm's law. Instead of I equals V over R of a resistor, I equals V times G. The current through a resistor equals the difference in voltage across it times its conductance. The units of G are certainly the most delightful and giggling-inducing units that we study in physics, because it actually has not one but two units. The units of conductance are Siemens, or, and this is really true, mhos. A mho, like an ohm for a resistor, backwards is a mho. That really is a unit of conductance. Great. Now let's not do that example. All right. I love this problem. If you understand this, you will have overcome one of the two greatest difficulties in this unit. This is the same battery, or the identical batteries, in two different situations. In the first situation, it's connected to one light bulb. In the second situation, the battery is connected to two light bulbs, one after another, in series. Which is brighter, A or B, and why? I'd like you to think about it. And if you feel like you have the right answer, I want you to also see if you can generate a wrong answer that is very tempting to make. Pause the video, come up with an answer, and talk to your neighbor. Pause. Okay, here's the answer. Here is something that is very tempting to say. Oh yeah, well, it's the same battery in both situations, so the same current has to flow, and so that means that bulb B is exactly as bright as bulb A. No, false, not true. Why is it not true? Because it's not true that the same battery will always produce the same current. That's not what batteries do. What did we say batteries do? Batteries always produce the same, no matter the circumstance. A battery will always produce the same difference in voltage between its negative and positive terminal. That does not always result in the same current, just as the strength of your lungs does not always result in the same air current. Battery always supplies the same difference in voltage, not the same current. The more resistance the battery is fighting against, the less current it gets from that same strength of the battery, the same voltage of the battery. When you have, let me give a this a little bit more room here. When you have these two light bulbs in a row, this B and C, one after another, that's like having two straws end to end. Note that the wire note that the wire is not like a straw. The wire has no resistance, or it has approximately no resistance. It is a very good conductor. But B and C, those two bulbs, are like end-to-end straws. More resistance in this case than this case. So less current flows through the circuit in this case with B and C compared to A. So bulb B is dimmer than bulb A. All right, one more thing that I want to talk to you about, and then we'll be done with this video. I'd like to talk to you about the power that is dissipated by a resistor. If you leave your iPhone light on too long, what happens? It causes the world to explode. No, it doesn't cause the world to explode. It causes your battery to run out of stored energy. So in your iPhone battery, there is energy stored in there, and when you leave your iPhone light on for a very long time, the battery converts the energy from being stored electrical potential energy into energy that has been dissipated as light and heat through the light bulb. What am I saying? I'm saying that resistors, including light bulbs, dissipate energy as heat. Let's figure out the power that is dissipated by a resistor. Now, you may not remember, or hopefully you do remember, from our unit when we talked about energy and power. The power that is dissipated or output by something is the amount of energy that changes forms per unit time. So I'm actually going to skip the derivation here, but you can look through it if you want. The power that is dissipated by a resistor is equal to the current through it times the voltage difference across it. The power dissipated by a resistor. Conceptually, what's going on? If you have a light bulb, it is converting energy from, so you might think of it as like kinetic energy of the electrons flowing through it into light energy that is leaving the light bulb. How much energy is it converting per second? The answer to that question is the power that is being output. 1 joule per second of converted energy, as you may remember, is 1 watt of power. If you put out 5 watts of power, that means you're putting out 5 joules of work each second. You're changing 5 joules of energy from one form to another each second. And what's going on here in a circuit like this, let's ignore this charge dq there, is that a battery is always putting energy into the circuit, and a resistor is always taking energy out of a circuit. If you substitute the Ohm's law expression into this expression for a resistor's power, you can find equivalently that the power output by a resistor is the current through it squared times the resistance. And if you substitute Ohm's law into it a different way, you can find that another expression for the power output by a resistor is V squared over R. You remember what else was equal to V squared over R? Centripetal acceleration was equal to V squared over R, where V was equal to the amount of velocity an object had around a circle, and R was the radius of a circle. Here, this has nothing to do with that V squared over R. The power output by a resistor is the square of the difference in voltage across it divided by the resistor. Now, remember I said that a battery was always putting energy into the circuit. How much energy does the battery put into a circuit per second? What is a battery's power output? It is also equal to the current through the battery times the voltage difference across the battery. But it is not equal to I squared R or V squared over R because there's no R associated with a battery. All right, so here is a problem that I'll encourage you to take a look at and then pause the video and try and complete. And if you have a neighbor, convince your neighbor that you're right. A stove heating element produces 3.2 kilowatts of heat power when connected to a voltage source of 240 volts. Draw a circuit diagram and label what about the circuit you drew is 240 volts. And please solve for the resistance of this stove heating element. By the way, do you expect it to be a very low resistance or a very high resistance in order to put out enough heat as thermal energy to heat the pan that cooks your food? This is really how stove heating elements work. It passes current through a resistor that dissipates energy as heat, and it puts out a certain amount of power, a certain amount of energy each second. Solve for R. Pause. Okay, here's the answer. Let me make sure that my head is not occluding the answer. Okay, so here's a circuit. There's some voltage source that has an EMF of 240 volts. It's attached to the resistance of the stove element. The power is equal to V squared over R, the power output by that resistor. Why did I choose that expression instead of IV or I squared over R? Well, because we know something about the voltage being applied to it, and we're talking about the resistance of the element. That's what the problem is asking for, and we're given the power that it is dissipating. So that's the equation that directly links those three. Mathematically, 240 volts squared divided by 300 watts is 18 ohms. That is a very low resistance. You probably want, if you're designing a stove, to have a high power output, so you'll choose a low resistance to be in that denominator and create that high power output.